Welcome to Get Your FRQ On. This question is from 2005. It's question 2, and it is calculator active. In the question stem, we have sand being removed from a beach by the tide and a pumping station adding sand to the beach. Sand is being removed by the tide at a rate of R of T cubic yards per hour, and sand is being added to the beach at a rate of S of T cubic yards per hour, and those functions are defined in the question stem. In addition, we're given that this model is good for t equals 0 to 6 hours, and that at t equals 0, there's already 2,500 cubic yards of sand on the beach. In part A of the question, we are asked to determine how much sand is removed from the beach during those 6 hours and to provide units. Well, if we have a rate at which sand is being removed, the total amount of sand removed in those 6 hours is just the integral from 0 to 6 of that rate. So if R of T represents the rate at which sand is being removed, we just need to do the definite integral of R of T between 0 and 6. All right, so we have the integral from 0 to 6 of R of T dt. We can substitute in the actual function. It's 2 plus 5 times the sine of 4 pi t over 25. And because this is a calculator active, there's no reason to try to do this integral by hand. Just define the function R of t in your graphing calculator and let your graphing calculator do this work for you. The value of this integral from 0 to 6 of R of t dt is 31.816, and since we're dealing with cubic yards of sand, that would be the unit. It would be 31.816 cubic yards of sand is removed from the beach over that 6-hour period. In part B, we are asked to find a function y of t, which gives the total cubic yards on the beach at time t. The function S of t represents the amount of sand being added to the beach. The function R of t represents the amount of sand, or the rate at which sand is being removed from the beach. And at time t equals 0, there's 2,500 cubic yards of sand already on the beach. So a function that represents how much total sand is on the beach at any given time would have to take into account all three of those pieces of information. Right, so the total amount of sand on the beach at time t can be found using a definite integral. All right, so y of t would be the amount of sand on the beach at time t equals 0, which is 2,500, plus the integral from 0 to t of s of x minus r of x dx, which would just be 2,500 plus the integral from 0 to t of 15x over 1 plus 3x, minus the whole function 2 plus 5 sine of 4 pi x over 25 dx. And then notice the change of variable here. Because y of t is a function of t and t is actually one of the bounds of our integral, we don't want the variable inside our integral to match one of the bounds. That doesn't make a lot of sense. So typically what we would do in this case is just swap out the t from the functions s of t and r of t and just use what at this point is a dummy variable. It could have been any variable, just not t. But typically we would use x here since we weren't using x before. So that just alleviates some of the ambiguity if you accidentally try to use t for both an upper bound, or a lower bound for that matter, and t as the variable that's being integrated here. It's just better to switch that up when the variable that you are actually interested in is one of the bounds of your integral. Then just use a dummy variable in your integral, and you should be fine. In part C, we are asked to find the rate that the total sand on the beach is changing at time t equals 4. All right, so the rate at which the total sand on the beach is changing must account for the sand being added and the sand being removed. Okay, well, y of t, the function we just found in part B, has already been defined as the function that represents the amount of sand on the beach at time t. So what we're actually looking for here is just the value of the derivative of y at t equals 4. Okay? So y prime of 4 is just the derivative of our y of t function, which was 2500 plus the definite integral from 0 to t of s of x minus r of x dx. But this is really just an issue for the fundamental theorem of calculus. All right, so the derivative of this function is just going to be s of x minus r of x. But we're interested in the value of this function specifically at t equals 4, or x equals 4. So we're just going to do that. We're just find s of 4, r of 4, find the difference. All right, and again, this is a calculator active question, so please do not waste time trying to do this by hand. Let your calculator find this value for you. Y prime of 4 is just s of 4 minus r of 4. S and R have both been defined in the question stem. You can find those values directly using your calculator. And y prime of 4 turns out to be negative 1.909 cubic yards per hour. In part D, we are asked on the interval from 0 to 6, what time t is the sand at a minimum, to find that minimum value, and then to justify our conclusion. Right, so by inspection, r of t and s of t are both continuous and differentiable on the interval from 0 to 6. R of t is a trigonometric function involving sine. Sine has no discontinuities. S of t is a rational function where the only 0 in the denominator is a negative value of t, so that we don't have to worry about that. So r and t and s of t are both continuous, and they are differentiable by definition. This implies that our function y of t is also going to be continuous and differentiable on the interval from 0 to 6 as well. Kind of nice to know. All right, so our function y of t can have a minimum value either at the endpoints t equals 0, t equals 6, or some value of t between 0 and 6 such that y prime of t is equal to 0. Okay. So we can figure out when y of t, the derivative of y of t is going to be equal to 0. This is a calculator active question. We can use our calculators to do that. Y prime of t is equal to 0 when t is 5.117865. And I do want to point out the added precision here. Because we're using a decimal at an intermediate step in this problem solve, it's best to be more precise than you need to be for a final answer, because if we start using decimals that have been rounded a little bit too much, that can throw off our final answer. And remember, our final answer has to be correct to 3 decimal places, either rounded or truncated, either one. And if we round too soon in this process, our final answer can be affected by that. So if we're working on an intermediate step, it's best to write those decimals down with more precision than is actually required, just so that it doesn't come back and throw us off later. All right, so we can figure out what the amount of sand is at all 3 of these times. We're given in the question stem that the amount of sand on the beach at t equals 0 is 2,500. Okay. We can use our calculator to determine the amount of sand on the beach at t equals 5.117865. That's 2,492.3694 cubic yards. And we can figure out how much sand is going to be on the beach at t equals 6 hours. Also, we can do that on our calculator. That's 2,493.2766 cubic yards. All right, and now that we have all 3 of these values, it's just a matter of, well, which one is the smallest? Well, that would be 2,492.3694. And that occurs when t is equal to 5.117865. That value of t you could round to either 5.118 or truncate it to just 5.117. That would be fine. And then the minimum value you could round to 2,492.37. I'm sorry, 0.369, or truncate it. You're going to get the 0.369 either way. All right, so the minimum amount of sand occurs when t is equal to 5.117865, however you want to handle that. And the amount of sand on the beach at that time is 2,492 cubic yards plus that 0.369.